Have you ever wondered how engineers determine the exact curvature needed for eyeglasses or camera lenses? The lens maker's formula is the fundamental tool that relates a lens's physical geometry and material properties to its focal length. Our goal today is to derive this famous equation. By understanding how light refracts at two distinct spherical surfaces, we can predict exactly where a lens will focus light based on its shape and material. To simplify our derivation, we assume a thin lens where the thickness is negligible compared to the radii of curvature. We place an object at point O on the principal axis, ready to trace its path. Light first encounters the front surface of the lens. As it moves from air into the glass, it refracts toward the normal. We treat this as refraction at a single spherical surface with a radius of curvature r1. The first surface forms an intermediate image at distance v1. Using the spherical surface refraction formula, we relate the object distance u and image distance v1 to the refractive indices and the first radius r1. Now, the light exits the lens through the second surface. For this second refraction, the intermediate image I1 acts as a virtual object. The light moves from the lens material back into the surrounding air. The final image is formed at distance v. Applying the refraction formula again, we note that the object distance for this stage is the image distance from the first stage, adjusted for the lens thickness. To find the total effect of the lens, we add these two equations together. Notice that the term involving the intermediate image distance v1 appears in both equations with opposite signs, allowing them to cancel out. By adding the equations, the intermediate image distance disappears. This is a crucial step because it removes the internal details of the lens, leaving us only with the initial object and final image positions. We factor out n1 on the left and n2, n1 on the right. Note that we flip the sign of the second radius term to make the subtraction consistent. This brings us closer to the standard form. If the object is at infinity, the rays are parallel and meet at the focal point. Substituting u equals infinity and v equals f into our equation allows us to define the focal length of the lens. Dividing by n1 gives us the lens maker's formula. When the lens is in air, the relative refractive index is simply n. This powerful equation links the focal length to the refractive index and the radii of curvature. Let's apply this. For a symmetric biconvex lens with radii of 20 cm and a refractive index of 1.5, we plug the values in. Remember, R2 is negative because its center of curvature is on the left. The calculation yields 1 over f equals 0.05, meaning the focal length is 20 centimeters. The lens effectively converges light at a distance equal to its radius of curvature in this specific case. What if one side is flat? For a plano-convex lens, the second radius is infinity. Since 1 over infinity is 0, the formula simplifies significantly, depending only on the curvature of the first surface. To summarize, the lens maker's formula is derived by treating the lens as two refractive surfaces. It shows that focal length is determined by both the material's refractive index and the physical curvature of the glass. Think about this: if you put a glass lens in water, the refractive index ratio decreases. This makes the lens less powerful, resulting in a longer focal length. Understanding the ratio is key to underwater optics. Whether designing a microscope or a pair of glasses, the lens maker's formula is the bridge between physics and practical engineering. Thank you for watching this derivation. Generated by Vision Solve AI.